Good morning, students. So today we are going to see what are the important properties of biomass with, with respect to our biomass conversion technologies and one of the conversion technology that is biomass briquetting. So before going to the biomass properties, let's have a very short rewind about the topic biomass that we already seen in our last sessions. That is what is biomass. So biomass is a plant material which is derived from the photosynthesis process. Photosynthesis process means combination of carbon dioxide in the air with the water and the sunlight and the chlorophyll which is present in the green plants to form food for the plant materials, that is especially in the form of carbohydrates, that is the building block of the biomass materials. So we already discussed the what is the efficiency of a photosynthesis process. It is having only theoretical efficiency of 6.6 percentage, but practically it is having an efficiency ranging in the range of 1 percentage to 2.3 percentages. So the solar energy is the only input energy in our world is concerned, and the photosynthesis only is the only one process that transform the solar energy from the energy spectra to our living mm, spectra is the photosynthesis process. And let's see what are the major important characteristics of biomass as our biomass conversion technologies is concerned. So there are a list of properties which among I would like to discuss among these properties, which include moisture content, calorific value, proportions of fixed carbons and volatiles, ash or residue content, alkali metal content, cellulose or lignin ratio. So let's see one by one in details. That is, first is moisture content. So moisture content will have two parts, that intrinsic moisture content and extrinsic moisture content. So as the name indicates, intrinsic moisture content is the moisture content which is not considering any weather effect on the plant, or we can simply say it is the amount of water present in the material without any influencing of the weather. Without, we are not considering the weather effects, whether it is a rainy season, whether it is a dry season, we are not considering the weather effect, just the moisture content present in the material. Okay, so that is intrinsic moisture content, whereas an extrinsic moisture content, as the name indicates, we are also considering the prevailing weather conditions during the harvesting on overall biomass moisture content. If during the harvesting it is a rainy season, then we have to consider that also into account. And if your harvest is taking place in a dry season or in a summer season or any other season, we have to consider that one also also. So that is the moisture content, and for our experimental values we always considered about the extrinsic moisture content, and because the intrinsic moisture content is not applicable under laboratory conditions. Next is calorific value. We all know the value means calorific value definitions. That is the heating value of a product, which is, or we can say that it is a heat which is released during the combustion process, or when the material is burned in the air. What is the amount of heat which is released from the material is called a calorific value, and it is usually represented as energy content per unit mass or unit volume of material, and hence we can mention it as a megajoule per kg. And or if it is in a volume, megajoules per kilocalories per liter, or unit volume we can consider. So calorific value is of two type of calorific value as far as our part is concerned. One is gross calorific value and net or higher heating value. So, and net calorific value or lower heating value. So gross calorific value is that we already mentioned what is calorific value, right? So calorific value is the amount of heat energy released when a material is burned. So you know that when a material, especially a biomass material, is burned, definitely that material contains some amount of moisture content in that material, right? So when it is burnt, what happens is that the moisture content will also removed from the material. So moisture is removed first. The moisture is in the liquid form will remove to the gaseous, means gaseous form. So when a liquid or moisture which is present in the material is converted to moisture vapor form, there should be a latent heat of vaporization should be used. So that latent heat of vaporization which is used is taken from the heat energy which is released during the combustion process. So a part of the combustion process, say we are burning a 5 kg of material, a 5 gram of material, and in that 5 gram of material only 1 gram is water. So when the 5 gram material start to burning, some energy is released, and that energy, a part of that energy, say 5 calorie of examine only, 5 calorie of energy is released. In that 5 calorie of energy, 0.5 calorie of energy may be utilized for converting this 1 gram of water to vapor. So that zero point 0.5 calorie is actually our loss when we consider the net calorific, means the gross calorific value. So what we are doing is that, so when a material is allowed to burn in the presence of air, we will collect the flue gases during the burning, and then we will allow that flue gases to cool to the atmospheric temperature. What happens when that, so that is we are collecting the steam which is escaped from the material, and then we are allowing the steam to cool down to the atmospheric temperature so that it will become water. So how much amount of water we collected there, we from there we can calculate it how much amount of vapor is converted, water is converted to vapor. So that we know that how much amount of energy is utilized from the heat energy to converting that water to vapor. So we are adding that latent heat of vaporization or condensation also into our account of our heating value. So that is the gross calorific value. So number of heat units released when unit weight of solid or liquid fuel or unit volume of a gaseous fuel is completely burnt and the products of combustion are cooled to 15 degrees Celsius, thereby condensing the water vapor present in. So when we condensing the water vapor present in, say we will get 1 gram of water will be get in that the condensation. So for we are considering the latent heat of condensation of or condensation for that water which is there 1 gram of water, and that we add to the calorific value. So because our in our total calorific value, that is that vapor heat of condensation is being utilized for vaporizing the water which is initially in the material. So hope it is clear. A net calorific value or lower heating value is simply the amount of heat which is released during the burning. We are not going to collect any product of combustion or flue gases. We are not going to cool to 15 degrees Celsius, and that we consider is at lowest energy itself. It's a lost energy, and we are not considering that into our account. So the net calorific value is the gross calorific value minus the latent heat of condensation of the water vapor present in the products of combustion. Numerically, it is the gross calorific value minus the latent heat of condensation, or theoretically, it is simply the amount of heat energy released when a material is burned without considering the moisture escape from the material. So next is proportions of fixed carbon and volatiles. So if you consider a biomass, it contains two parts. One is fixed carbon and another one is volatiles. Volatile is the material that is converted to vapor when the original biomass is heated. So when the original biomass, when a set of biomass is taken and is heated, so initially some part volatiles will vaporized and will remove from the biomass itself. So that is called volatiles. The material which be converted to gaseous form when the heat energy is applied or when a material is heating is called volatile matter. And the leftover after escaping the volatiles, what is left there in the biomass is called a fixed carbon. So volatile content or volatile matter is a solid fuel, is that portion which is driven off as gas including the moisture by heating the product to 950 degrees Celsius for almost 7 minutes. So that is called a volatile content, and fixed carbon is the mass remaining after the release of this volatiles excluding the ash and moisture content. We won't use the ash as the part of this fixed carbon, and moisture content. Moisture content will always driven off will when it is heated up to 950 degrees Celsius for 7 minutes. Okay. Next is ash or residue content. As the name indicates, we all know that when we burning our biomass stove in our home, most of the house may be now equipped with biomass stoves, or in earlier it was there. Now I think most of the houses shifted to LPG or any other type of cooking media. But when we see that when in a biomass stove, when the wood is completely burnt off, the leftover in the stove is only the ash. So ash content is the incombustible part of the biomass which is left over after the completely burning of the biomass. So chemical breakdown is a biomass fuel either by thermochemical or biochemical process produces solid residue. So in this case, we are consider both ash and residue content. So when a material is undergoes a thermochemical process, the remaining portion is called ash content. And when a process is undergo the biochemical process, example, the biogas generation or anaerobic digestion, what is left over is called a residue content, a solid liquid residue. So when it is produced by combustion in air, this residue is called ash and that forms a standard measurement parameter for solid and liquid fuels. It affects both handling and processing cost of the overall biomass energy conversion. And if the metal is undergoes the not biochemical process, then the leftover is called residue. So we know that when a same material is taken and burned, and when that same material is feed into a biogas plant, and the end of the biogas plant, we will get the slurry from the biogas plant. So the slurry will be more in volume than the ash. So when the same materials undergo the biochemical process and thermochemical process, the residue which is left after the biochemical process, that is anaerobic digestion, will be more than that of the thermochemical process. That is the last sentence here. During biochemical conversion, the percentage of solid residue will be greater than the ash content formed during the combustion of the same material. Then alkali metal content. Alkali metal content including the sodium, potassium, magnesium, phosphorus and calcium. So it is very important in case of a thermochemical conversion process is concerned. And why it is important is that these alkali metals when it is combined with the silica which is present in the material will produce a sticky ash. That sticky ash will maybe there is chances to that sticky ash will block the airways to the furnace and boilers uh, in the commercial burning process. So we have to take care of this alkali metal content. Next is cellulose or lignin ratio. It is very important when it is considered in a biochemical conversion process because the lignin is a material which is very hard to digest. It is very hard to go for anaerobic digestion or for decay. So the biodegradability of cellulose is greater than that of lignin. So it was we always go for a very easy decaying material for go will should be taken for the anaerobic process or biochemical process. So cellulose containing material is more suitable than the lignin content ratio, lignin content material. So it is important of knowing this ratio. So next we can go to the briquetting. So briquetting means we are densifying the material into a smaller unit. We know that if material is harvested, for example, if the rice is harvested, we will get rice straw, right? So rice straw, when it is dispersed in a very vast, very randomly, it will take a very and it requires very lot of space. If we are compressing it together, it will compact together. The air will be removed from that air space, then voids will be removed from that. It will form a compact form. So that will be easy for handling. That will be more, having more energy density, and it is convenient to store and convenient to transport all of this, and hence we are that particular form after densification is called a biomass briquettes. So briquetting is a densification or compaction of the residues into a product of which is higher density than the raw materials. So this is a briquettes. Example of briquettes is cylindrical briquettes. So it can be used either for heat generation in households and small scale industries or even for power generation in large industries. So briquettes, why we require for briquettes is that the direct burning of biomass is inefficient. So only direct burning will give an efficiency of only 10 to 12 percentage efficiency is only there for direct combustion of biomass materials, and it is also the energy density in biomass material is very less. So for getting some amount of energy we have to burn a large amount of biomass together, and the storing of this large amount of biomass in a single room is also requires more space. So all those considering all those factors, we can compact this together to form very inefficient efficient more efficient than the direct burning, and also easy for handling, transportation, stored, etc. So that's why we for the biomass briquetting. So what are the advantages of briquetting? What are the applications of briquetting? We already mentioned some of this. It is convenient for storage and transport, ease of charging the furnace, and it is having a uniform shape and uniform size. If you're going for briquettes, it's having uniform size and uniform shape, so it is very easy to handling and transporting, storage, and easy for charging to the furnace. Improved characteristics of gasification and reduction of entrained particulate emissions. Then uniformity in size and shape, good substitution for natural fuels, worldwide availability. Especially, we are making the biomass with the locally available material. We are not going for any imported material to make a biomass briquette. So, whatever biomass which is abundantly available in our area, we are going to prepare briquettes with that material only. So, it is applicable in the worldwide, especially in the less developed countries where more amount of this biomass waste is available. Low cost of the machinery, overall fuel cost for users as they are made from biomass waste, job opportunities, savings time, and decreasing local deforestation rates. So then we can see what are the materials which can be used for biomass briquettes. So we can use the charcoal dust, that is the dust which is produced from charcoal. Then sugar cane bagasse, that is the cane, the material of sugar cane left after the removal of entire juice. Then coffee husk, then rice husk, then water hyacinth, sawdust. So these all materials can be used. Many type of materials which is solid in nature and can be used to form briquettes. So there are more examples there here. Sugarcane bagasse, charcoal dust, coffee husk, gum arabia, tree leaves, water hyacinth, rice husk, sawdust, and other wood residues or agricultural byproducts can be used to make briquettes. So how the briquettes process is done is that, so we are applying a high pressure into material, and there when the pressure is increasing, the temperature also increasing because of the application of this high pressure. So when high pressure is applied in high temperature, then the cellular structures with the material will release a lignin content which is present in that material. So lignin will squeeze out of the material, and that lignin will act as a binding agent to hold these materials together as a single unit, like a gum, or like it will provide an adhesion, and hence the material will all will binds together and it as a single unit. So depending upon the type of material and the pressure applied, and the type of binder material is used. If the lignin content is not naturally present in the material, we can add any extra binder material for proper binding of the things. So all those things are there. So the under high pressure, the binding mechanism can be divided into adhesion and cohesive forces and attractive forces between the solid particles and interlocking of the bonds. So so that is how it is working. When the high pressure is applied, the temperature is increased. So during the simultaneous application of high pressure and high temperature, the lignin which is present in the material will squeeze out, and that lignin itself will act as a binding agent or adhesive agent to hold the materials as a single part, and it will form a definite shape. And if naturally lignin is not present, we can add an external binding agent to make it more convenient for handling and storage. So, according to the brick type of presses used, briquettes can be categorized into five: piston press, screw press, roller press, and pelletizing and manual presses. Then, on the basis of the pressure used, high pressure compaction, medium pressure compaction assisted by a heating device, low pressure compaction with a binding agent. So this is how the processes proceeds. That first we collect the raw material, then we'll dry the material to suitable moisture content, then we will go for the size reduction to the suitable size, then we will add to addition of suitable binder if required, then we will mix it properly, then we will briquette by the compressive force, then drying of the briquettes, and it is ready for usage. So next we can see what are the applications. We already discussed a lot of applications, which including the cooking and water heating in households, heating of productive such as tobacco curing, tree dyeing, poultry rearing like ഉപയോഗിക്കാം. At the same time, it can also use the firing ceramics and clay wares such as improved cook stoves and pottery bricks, etc. Then it can be used as a fuel for fuel in gasifiers to generate electricity, and also it can be used to power the boilers to produce steam, and it can be have any many applications, especially in the countries of US, Australia, Japan, Korea, Taiwan, and also in European Union. And the public participation in urban cleanliness and the conservation of tree and forest covers. The limitation is that only solid fuels can be used to produce a briquette. So it doesn't have any application in like liquid fuel application or gaseous fuel applications, especially it do not have any application in IC engines. And the cost of screw or die screw press and its repair is also one of the barriers in the briquetting technology. Then we have to store the materials which is covered, otherwise moisture may comes inside the um, briquettes that may affect the physical nature of the products, and that will lead to easy decay of the briquettes. So low carbon content of the briquettes limit the temperature which is achieved from this briquettes is maximum to 1000 degrees Celsius, which may not suitable for most of the industrial applications. So that's about the today's presentation. Hope it is clear. In case of any doubt, you can contact me through WhatsApp, or you can discuss by call. You can call me also. Thank you.